Hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our 61st, can you believe that already, 61 CoCoRaHS Weather Talk webinars. This is our 61st. We want to thank you for being with us today. I'm your host, Henry Regis, and running the technical side of our program is our very own Noah Newman, who's been with us through most of our broadcasts. We're coming to you live from the Colorado Climate Center here at Colorado State University. And it's cloudy. I think we have a lenticular cloud over the sun right now, blocking out the sunshine. But here in Fort Collins, Colorado, a little chilly out there too. Hey, for those of you who are unable to join us for our live broadcasts, we're going to be recording this one for future viewing on our website. And all of our Weather Talk webinars are sponsored by generous donations from listeners just like you. Well, today we will be finding out about one of the most deadly elements of a hurricane or tropical storm, and or sometimes even a nor'easter in some cases, and that is the storm surge. You've most likely heard that term before. What it is, we're going to let you know what it is and what you can do to be prepared for when it strikes. We're very fortunate today to have with us Jamie Rhome. He's the acting executive officer and the storm surge specialist and team lead, a lot of titles there, at NOAA's National Hurricane Center in Miami, Florida. His group, he's in a group that specializes in predicting storm surge inundation heights, accompanying landfalling, tropical cyclones using sea, lake, and overland surges from hurricanes, the SLOSH model. And it's a computer model. We thank him for taking time out of his busy schedule today to join us for today's webinar. Well, Jamie, originally from Roanoke Rapids, North Carolina, if you're familiar with that part of the state, he received his Bachelor of Science and Master of Science degrees from my alma mater, North Carolina State University, and both of those are in meteorology. He joined the National Hurricane Center back in 1999. Among the interesting things he has encountered during his career was his selection for a temporary assignment to the White House's Office of Science and Technology Policy in 2008-2009, where he served as a scientific policy analyst with the Presidents George Bush and Barack Obama administrations. Well, Jamie, welcome. It's great to have you with us today. Good to see a fellow Wolfpacker out there, and we're so glad you can join us.
Oh, it's a pleasure to be here, and I trust you saw our basketball victory last night. It was a nail biter, but we pulled it off.
Well, it's great to see those. It's been a long time since we've won a national championship, but one of these days we'll be back there again, hopefully.
One of these days, not this year, but hopefully soon enough.
Yeah.
Well, thank you so much for the opportunity today. Actually, talking with the public and our partners and engaging someone outside the walls of my office is the most enjoyable part of my job. I wish we had time to do it more often. Obviously, you've got to run the organization, and so I only get to do about a quarter of my time this sort of work. So thank you for dragging me away from budget to do this sort of work. So we're kind of going to be talking about today about storm surge. And here's the outline of what we're going to walk through today. We're going to basically introduce you to what is storm surge and why should you care about it. Probably the part most people are really interested in is how do we forecast storm surge. We have this little black 8-ball that we shake. No, I'm kidding. So we'll walk through the modeling and the science of how we forecast storm surge, and then the products that would be available to you during a hurricane to enable you to determine if you are vulnerable to storm surge. So that's sort of the outline we're going to work with today. But first and foremost, we need to define it. What is it? And so storm surge in its simplest form is simply the ocean being shoved landward or overland by wind. The wind could come in all different forms. It could be a cold front, it could be a hurricane, it could be a nor'easter. It doesn't matter. The water doesn't matter. If you exert a force over the water, it doesn't know the calendar, and it doesn't know these definitions that we humans use. The water responds to the wind. Now, generally speaking, storm surge is most often attributed to hurricanes because the force of the wind in a hurricane is strong enough to push the water greater distances inland than just a routine storm. That said, when you get to big nor'easters like the one we experienced a couple of weeks ago, you will get storm surges in that case. So if you remember correctly, you got Boston had a lot of flooding with ice actually in the water during the event a couple of weeks ago. But storm surge is different from tide. So tide is the normal astronomical or due to the force of pulling and shoving from things like the moon and the sun. Happens twice a day in some areas, once a day, high tide, low tide in other areas. This is not storm surge, but it contributes to storm surge. So the two of these get together and they tangle themselves up. And so storm surge is a function of the tide. And so you have to predict the tide to predict storm surge. And so we have to somehow stitch these two together to come up with what we call the total water level, or what is the flooding you experience on land. Now, no area along the coast it can escape this. While the Northeast doesn't, you don't always think hurricanes in the Northeast. They have been impacted by past hurricanes, and so here's a couple snapshots of the Northeast to show you that they can be impacted by hurricanes. Probably the one most people remember is Sandy back in 2012, which was a real firm reminder that hurricanes can impact the Northeast. The other storm that is notably on people's mind, or really sort of defines the phenomenon of storm surge, is Katrina. The one thing about Katrina that can confuse you, though, is so much of the narrative with Katrina was focused on what happened in New Orleans, which, if you don't know, New Orleans sits below sea level and is basically encased in a barrier or walls which protect the city from flooding on a routine day. If it weren't for those walls, the city would just routinely flood all the time because it sits below sea level. Those levees were compromised during the event, which effectively allowed the bowl to fill up with water. You contrast that to what happened in Mississippi, which is the untold story in Katrina. So few people talk about what happened in Mississippi, which is the classic traditional storm surge where water is just shoved from the ocean inland. And this is a shot here. I actually toured this area afterwards. It's one of the more chilling things I've ever seen in my life, is to stand in a community that used to be hundreds of homes, an entire community, and look around and everything, literally everything right down to the slab is gone. And you can see that in this image. These are the remnants of a home, or the slab upon which they previously sat upon. And you can see that everything is gone. Literally looked like a big bulldozer just marched from the ocean inland. And when it stopped, it left a debris pile well over your head. Nobody can survive this. I mean, just look at this image and the force of the water. It cannot, no one can survive this. And for this reason, storm surge has historically been the biggest killer in a hurricane. So if you look back in history, 50% of the lives lost in a hurricane are due to storm surge. So I have good news at the end of this talk. We've actually moved the needle on that. But I think everyone can look at this picture and see why this is a big deal. We have to have some way in this country to tell officials that this is coming, where it's coming, and evacuate. You can't stay. You can't ride this out. And storm surge is the reason we evacuate for hurricanes. It's not because of wind, and people don't realize that. You'll hear a lot of talk about the Saffir-Simpson scale. It's a Cat 4, it's a Cat 5. Oh, because it's a Cat 5, now I'm interested. That's a wind scale. We don't evacuate for wind. We evacuate for surge. And that's one of the things in this country we have to work on, that misunderstanding, to make our evacuations better. Here's a case of Sandy, a little bit different. The houses are still here. So, but what you see is they've all been literally dumped on the floor or on the sand or the ground. So what happens here is the water rushes underneath them with so much force, the waves running and ripping, it basically rips the piling or the footing out from under the house and drops the house on the ground. So imagine if you're in this house, probably not good odds that you're going to survive this either. So yet another case, and remember Sandy was only a Cat 1, Category 1, so don't get enamored with that wind scale. This was a Category 1 hurricane, 73 deaths, $65 billion in damage. These are staggering numbers for a system that was only a Cat 1. If you're basing your analysis of a hurricane or the severity of a hurricane on that Saffir-Simpson scale, you're going to miss the mark. That's just not the best way to assess your vulnerability. Looking at Hurricane Ike, so I'm sort of going around the country here, so I'm not leaving anybody out. Looking at Hurricane Ike, this is 2008, Bolivar Peninsula, Texas. A similar scene here. You see everything just wiped right down to the slab. You see these little squares here are where homes used to sit, and in some cases you can't even find them. If you look closely here, you can see the remnants of a little road that would have gotten you off the main road back to the community. There's just one house that is standing. This is a very famous story about this house, if you wish to look it up, a very interesting engineering feat. I think this speaks to building codes and what building codes could do for this country if we were to embrace them. That's as far as I'll go on that political hot button issue. But anyway, you're not going to survive this. I mean, just look at this. You're not going to get out of that. And so, again, establishing the need for evacuations. I'm going to do a quick before and after here, and this is in Waveland, Mississippi. I want you to frame this big tree. Use this big tree to sort of frame where you're at, and when this before and after. Again, not survivable. Here's a case from Hurricane Sandy. This is East Village, if you're familiar with Manhattan. So this is a before, and this is what it looked like during Sandy. Now, there's another myth that really gets people in trouble in a hurricane. So you're going to look at this image and you're going to say, well, that's about up to the wheel well of that bluff here. I could easily wade through that, or I could easily just go up a floor, and this is no big deal. Why do I need to evacuate? Well, imagine if you had a heart attack or a medical emergency in this phenomenon, and you needed to call 911, and they couldn't get to you because the roads are flooded. Then it becomes a much, much, much different debate. Indeed, you see people down here wading through this water, and this is not smart to do because there can be all sorts of debris and junk in the water. You could step into the manhole covers typically pop off the road opening, and you could step in it and fall into incredibly deep area. But think about it from the point of view of if you need emergency assistance, it cannot get to you. Also, we have these things in this country called power lines, and they tend to go down in a hurricane. So now you've got salt water, standing salt water, and live power lines. They don't go well together. And if you've got a live power line laying in this water and you wade into the water, that's not good. You're not going to have a good day. We've heard and seen several examples of the first person would get electrocuted, the next person would run into the water to try to save them, that person would get electrocuted, the next person would run into the water to try to save the first two people, and that person would get electrocuted. So bottom line is you don't want to be in the community that gets flooded like this, even if the water is not deep enough to scare you. It's just, trust me, it's just more dangerous than you can envision. And that's my role in life, is to educate this country on that threat and to prepare them for the next one. All right, so we've kind of gotten through the elevator speech here of why you should care. So now we have to look at, well, what causes storm surge and what are the factors that go into it and how do you predict it? Turns out it's a shockingly more complicated phenomenon than one would think, and certainly more complicated than I thought when I said yes 10 years ago, taking the job. There's so many parameters that go into this. The intensity of the storm is the obvious one, But the forward speed, and by forward speed, this is not the intensity of the storm. This is how fast the storm is approaching land or approaching a community. So it's how fast the storm is moving along. The size is incredibly important, almost, and in some cases more important than the intensity. And this particular parameter of a hurricane is very difficult to predict. This is, while we've made great strides in predicting track or where a storm will go, we still have a lot of work to do on predicting size. The angle at which it approaches a coastline is really, really, really important. Irma in southwest Florida was yet another example of the extreme sensitivity to just a very subtle change in the angle of approach. The width and slope of the continental shelf, and by this I mean how fast does the ocean get deep as you move offshore. So in places like Hawaii and Puerto Rico, the depth of the ocean drops immediately as soon as you move offshore, whereas in other places like the Gulf of Mexico, I don't know if anybody here lives on the west coast of Florida, but you can get in a boat and drive forever off the west coast of Florida and the water's still 12 foot deep. So those features come into play tremendously. Local features such as the presence of bays and rivers and islands and all sorts of things. In North Carolina, where I sort of cut my teeth growing up on these coastal storms, is a real difficult place to forecast because it's got all these things going on. And I put central pressure here because people get hung up on this one. People think central pressure is a big contributor. So the analogy that I hear people say is it's like the low pressure just lifts the water up like if you were sucking a soda up a straw. It turns out that central pressure is not a big contributor to the total water event or the total flooding. So if you look here in this little animation, the wind literally forcing the water towards the shore is the primary contributor. So I wouldn't get hung up in this low pressure thing. It's a small contributor. Our models know about it. It predicts it. We include it. This is just one of those things that distracts people quite a bit. It's just not a huge player in storm surge. And here's our North Carolina example. When you make a forecast, you've got to somehow stitch all of this together. You got, in some places, the winds are blowing offshore, blowing the water away from land. In the other part, you got the winds blowing onshore towards the land. You've got all these features such as bays and barrier islands going on. And so it becomes quite a challenge in real time to do this and to make this forecast. So with that, I'm going to sort of evolve into how we make our storm surge forecast here. And so making the perfect storm surge forecast, well, it doesn't exist. I've been doing this for, 18 years, and I've yet to make, see, or witness a perfect forecast. Now, the public in Congress expects us to make a perfect forecast. So we always go through this every year, only profession in the world where you can be wrong 50% of the time and still keep your job. We're sort of the butt of that joke. But I'm gonna try to prove to you today that it's virtually impossible to make a perfect forecast, and that we have to live with the uncertainty of forecasting, especially hurricanes, which are fickle. We have to, as a nation, live with this uncertainty and just learn to deal with it. All right, so the weapon of choice we use is a model called SLOSH, stands for Sea, Lake, and Overland Surges for Hurricanes. It's actually been around for a while. It's a computerized numerical model, so if you're used to hearing about atmospheric models, you'll hear about TV broadcasters say, the GFS forecast or the European model or these sorts of things. It's kind of similar in that it's solving equations, lots of math, except instead of solving equations for the atmosphere, it's solving equations for a fluid, in this case, water. And so the model is pushing water around as a result of the hurricane and then giving us a forecast. Now, I wish it was that simple. We just hit a button and SLOSH would kick out a number and we could go with it. But it's not that simple. Efficiency is the name of the game. So imagine if, and I'm going to give you a hypothetical. Imagine if in the height of a major hurricane approaching land, the White House called and asked for a briefing, and I responded, I'm sorry, I can't give you a briefing today. It takes my model 18 hours to run. I'll give it to you tomorrow. Well, I'd probably be fired for that response. When it comes to hurricanes and the types of decisions that people are making, evacuations of major cities and such, you have to be quick. You have to be responsive. You have to be able to answer questions when they come to you, which means the model has to be fast. And the way we make the model fast is, let's say, for example, a hurricane is coming here in Texas. You wouldn't want us wasting any computer power up here in New York. That would be ridiculous. So we build the model in these discrete little blocks here, as you see with these little gray areas. They're called grids, such that we only have to run the model where we need it. So if there's a storm coming in here in Texas, for example, then we might only use these two grids here. And then we don't waste any power using, computing a null answer up in here. It turns out to make the model incredibly fast. It makes it hard to manage, but it makes the model incredibly fast and efficient. And so that's the name of the game. So when you're making a forecast here, so let's go through this hypothetical. This is Irene, but this is a hypothetical. So there's the forecast, the track, the skinny black line, the cone, whatever you call it. There's where the best information says it's going to go down that little line. But in reality, you don't know if it's going to go exactly down that line. It might go a little to the left, or it might go a little to the right. And contrary to what anybody has ever told you, nobody knows which of those lines are going to happen. Now, you'll have people farming the internet and probably some people on this call who think they know which one of those lines are going to happen, or tell you they know which one of those lines are going to happen, but nobody knows. Nobody knows which of those lines is going to happen. And so we're forced, as forecasters and emergency managers and public responders and citizens, to consider all of those lines. We have to think, well, how do I protect myself or prepare my family if this line happens versus this line? And so that's how we forecast. And I'm going to show you an example. This is a little bit techy and sciencey, but I promise I'll take the edge off of it. So if you think back to Matthew, and don't worry about these scales and numbers right now. Just relax yourself to look at the overall image here. So if you look at Matthew was coming up the coast of Florida. So here's Florida. This is the St. Johns River. Here, Georgia, here's South Carolina, and North Carolina is off the map here. So remember, Matthew was coming up the coast here, and we're really worried about Jacksonville. So Jacksonville is right in here. So we're really worried about Jacksonville. But then there was this little wobble thing that happened. So you see it here. It kind of was approaching the coast, got stage fright, and moved over to the right a little bit, and then resumed its previous motion. So this little jog here, this tiny little bump, if we went back and pushed it over in the model, meaning this is what happened in reality, we went back and pushed that little dot back over and reran the model just to see what would have happened had that little bump not happened. It results in a difference of 3 feet. Now think about that for a moment. Nothing changed in the intensity, forward speed, anything. All we did is just ironed out that little bitty little tiny bump, changed the answer by 3 feet. 3 feet. That's up to my waist. That's the difference between your house staying dry and your house being completely ruined, at least the bottom floor of it. That's massive. And so that sort of gives you a sense of just how sensitive storm surge is to even the smallest, tiniest, subtlest of changes in the storm parameters. So how do we get around that? So we have a series of products here, and this is a little bit in the alphabet soup here, but I promise I'll walk you through it gently. We have what's called pre-computed products. Now, by pre-computed, I mean they exist now. They exist right now. You can go on the internet and get them right now. These allow you to assess your vulnerability to storm surge. So if you're just curious, you know, I have no idea. I don't know if I could be vulnerable to storm surge. This is what these products are meant to help you do. So we give these to federal, state, and local authorities at all walks of life to enable the nation to plan for and mitigate the impacts of a hurricane. So what you don't see in a hurricane is all the prep work that's happening now to prepare for a hurricane in 2018. So, you know, all across the government, they're looking at these products, and by government, I mean federal, state, and local, looking at these products to assess their vulnerability and put plans in place to help protect the populace when an actual hurricane comes. And we'll get into that a little bit more. Then when an actual storm forms, that's what this real time means. So everything above this line is pre-computed before a storm forms. Below this line is when a storm forms, we make a forecast. And so we're going to walk you through these products. All right, so let's start. You can tell I'm North Carolina biased here in my examples. Let's start with, and here's one of those little grids we talked about. You remember we broke the model up into little discrete chunks to make it quick. So here's a little track. If you can see right down here, this is a little track of a hurricane, and this is a hypothetical hurricane. It doesn't, you know, there's no hurricanes out there right now. So this is a hypothetical hurricane. This is a Category 3 moving west-northwest, 15 miles per hour, making landfall at high tide. These colors represent storm surge values. Clearly brighter colors equal bigger impacts. So I would say anything green and above here is bad, really bad. So this is the track, Category 3, west-northwest, 15 miles per hour, high tide. And in this little spot, the model says it's going to have 4.8 feet. In this little spot right there, 4.8 feet. This is just a zoom in. I'm really, really, really confident if this exact hurricane happened and went on this exact track, that little spot right there would get about 5 feet. The model has been proven to be accurate if given good meteorological input. Now, the question before us, though, is what are the chances of this exact hurricane, Category 3, moving west-northwest, 15 miles per hour, making landfall, high tide, going in that exact location? And it's actually quite low because the hurricane could be weaker, stronger, move in a different direction, move a different forward speed, make landfall somewhere else. So we have to somehow figure that out. We have to somehow figure out how to handle this. Well, let's add another storm track. So you can see I've introduced another track here. It's still the same Cat 3 moving west-northwest, 15 miles per hour, high tide. I just introduced another track. And I've introduced a third track, and a fourth track, and a fifth track. Now, if you're paying close attention, you notice this number here is slowly crawling up as these tracks get closer and closer to that particular location. You see this? And when you're all said and done, you basically fill the entire coastline with tracks. So you're basically striking the coastline at every location. Again, with Category 3, west-northwest, forward speed 15 miles per hour, high tide. So this is basically saying that the maximum surge that could occur at this location from this type of storm is 13.8 feet. Now the astute reader would say, oh, that's well and good and all, but all hurricanes that impact North Carolina are not Cat 3. They don't always move west-northwest, and they don't always move 15 miles per hour. So let's do it again, except this time let's add more tracks. And while we're at it, why don't we just hit the coast with every conceivable Category 3 that we can envision, and then determine what is the maximum storm surge that any Cat 3 could produce. It turns out for this little spot, it's about 15 feet. So this little spot, I hope there's nobody who lives there on the call. This little spot, the maximum theoretical storm surge, which could occur from any Cat 3, is 15 feet. And And so people are probably saying, well, that's interesting, but how in the world is that remotely useful? Well, what if there's a hospital here? Or what if there's a power plant here? Or what if there's an evacuation route here? Emergency managers, local officials need to know where the water could go, and more importantly, where the water can go. And why is that important? Well, if you have to open up a shelter for people to evacuate to, you want to make sure you open a shelter in a place that's going to stay dry. So you clearly you wouldn't open up a shelter here in this 15-foot of surge. You would open a shelter over here where it's high and dry. So now, when a Category 3 approaches North Carolina, we know, or at least local officials know, who to evacuate. We run transportation models to know how long it will take. We run analysis to know how many shelters need to be opened, how many roads need to be opened, do they need to reverse the lanes. We do all of this analysis before a storm ever forms. So all of this is set in stone via what's called a hurricane evacuation plan. This is done everywhere, not just for North Carolina. This is done everywhere from Texas to Maine. And this is what enables our country, more so than any other country in the world. We're the most advanced country in the world with this capability to have safe and efficient evacuations. If you don't believe that statement, we had four landfalls this hurricane season, three of which were major hurricanes. And as of right now, nobody died from storm surge in those 4 landfalls. Let me say that again. Remember how I started this talk? Storm surge has historically accounted for 50% of the lives lost in a hurricane. This hurricane season, the U.S. sustained 4 landfalls, 3 of which were major. And as of this moment in time, we have not discovered a death that was attributable to storm surge. That is a remarkable feat to report to you.
Jamie, let me interrupt you real quickly. Do you guys do this for other countries like in the Caribbean? I know Puerto Rico is part of our the Commonwealth with the U.S., but places like Jamaica or the Bahamas or so forth, do you run these at all for some of those countries down there?
It's actually a good question, and one that's near and dear to my heart. As of right now, the U.S. is the most advanced country in the world with this predictive planning and mitigation strategy. And all other countries have started to look to the U.S. At this business model as something to learn from and possibly mimic. I get requests from other countries, in some cases, very developed countries. And you know, they're interested in what we're doing here and how it works. And I'm happy to report that USAID, which is the arm of the government which assists other countries, is now working with us to test this capability out in other countries. And our first test is the Dominican Republic and Haiti. Haiti is in a very, very vulnerable country, very susceptible to hurricanes, and just because of the history of that country, there, you know, you really have the potential to lose a lot of people in a hurricane. So we're down there testing whether or not these capabilities can work in other countries. That project wraps up this year. So we'll, you know, in another year or so, we'll have sort of a report back on, you know, how much of this is portable to other countries. I can say that I've been to Japan, I've been to different places around the world, sort of talking to government officials and forecasters about what we do, because people are interested. So this is absolutely something the U.S. should be quite proud of, because I'll argue that we're the best in the world at this particular component. But great question. I hope I answered it for you.
Yeah, and I guess a quick follow-up to that, I noticed you're giving East Coast examples. So for the Pacific coast of the U.S. or Hawaii, California, and so forth, I know there's not a lot of direct strikes, but do you run these models there as well?
Not yet, but There is growing demand, growing interest in doing those areas, and we just finished Hawaii. We just finished Hawaii about 6 months ago. We finished Puerto Rico and the Virgin Islands a couple of years ago, so they had some of these capabilities for Maria. Southern California is an area that is expressing interest. Guam, Samoa, or other U.S. areas of interest. And so that's where we're at. I think for the next 4 or 5 years, we're going to be working at sort of plugging those gaps. The west, outside of Southern California, the west coast of the U.S. is not susceptible to hurricanes or tropical cyclones. They're more susceptible to winter storms and winter storm surge. And that's not my area right now. Winter storms, we are primarily constrained to working within hurricane-related areas. So there's probably more to come on that in future years, but as of right now, Southern California, Hawaii, Puerto Rico, and Virgin Islands, and then the rest of U.S. territories in the Pacific would be our primary thrust areas.
Okay, thank you. Cover it? Yeah, thank you very much.
So stitching this all together, and people either love or hate this triangle. I've never seen a graphic we've created that stirred people so much. But stitching it all together, you basically have planning and mitigation, which is happening right now. So right now, we're working with emergency managers and partners in the federal, family, and state and local authorities to help plan for this hurricane season. You know, do we have hospitals in vulnerable areas? Do we have shelters in vulnerable areas? Do we have enough road capacity to evacuate everybody out? How long does it take to evacuate everybody out? Some states have to pull the trigger at 72 hours before landfall, other states at 12 hours before landfall. Developing exercises, exercising those exercises, testing, planning, you know, we're all hip deep in that right now. And to those that think that the off season is easy, you know, the off season is almost as crazy and chaotic as hurricane season, because we're doing all of this for as many areas as possible. Then once a hurricane forms, you get into this sort of, so imagine a hurricane forms out in the middle of the ocean, but it's not threatening anybody. You get into sort of this readiness mode. That's sort of where everybody's like, oh, wait, it's hurricane season. Oh my goodness. So, oh, I better check my you know, make sure I've got batteries and, you know, these sorts of things. So you get into sort of readiness phase. And then at some point, you have to respond to the event, meaning you either have to evacuate, or you have to shelter your house up, or you have to, you know, bring in furniture from the back, or, you know, whatever. You've got to respond at some point. And generally, this is about, you know, give or take a day. This is about 2 days before landfall. That's generally how it breaks down. So this is, again, a little bit alphabet soup, but once a storm forms, so once we get into this area right here, this red and yellow, where it's, oh my goodness, it's hurricane season, it snuck up on us, there's a storm out there. The way we do things is with probabilities. Now, probably a lot of you hate probabilistic or probabilities. I don't think I've ever given a probabilistic talk that someone didn't want to throw something at me, but this is literally the only way to do it. And I'm going to seek to prove that to you here in a second. So we take this probabilistic storm surge and shorten it to P-surge. If you ever hear me say P-surge, this is what I'm talking about. So basically what we do is we take the official forecast. So the official forecast is the cone, or that little skinny black line. And then using our historical errors, so we kind of keep track of how good and how bad we are, we perturb or change that forecast to account for things like track differences, size, forward speed, intensity. I'm going to show this visually in a second. Again, these uncertainties or variations or scenarios, if you will, are based off our historical errors. They're not just randomness. They're based off how accurate we have and have not been in the past. And so it looks like the same graphic we showed before. Here's the actual storm. There's the official forecast of the cone or the skinny black line. We iterate or create alternate scenarios to the left and to the right. And you see how these spread out with time. That's because forecasts become less accurate the further out you get. So, you know, you witness this every day. A 5-day high temperature forecast is generally less accurate than a 1-day high temperature forecast. But the same is true with hurricanes. A 5-day track forecast is less accurate than a 1-day track forecast. So you see these scenarios fan out, and that's how we're taking into account that decrease in accuracy as you go in time. But we also have to take into account size. So we have to include different size storms because we don't predict size very well. We also have to take into account variations in its forward speed and variations in intensity. And then when you add it all up, you end up with what can be thousands of iterations. So it's not just one scenario, it's thousands of iterations. And then from that, you can back out a probability, meaning what is the probability of this hurricane impacting me? Now, let's face it, we live in a binary world. Binary means yes, no. You want someone to tell you you absolutely are or absolutely are not going to get impacted by a hurricane. That's what you want. The science will not allow anybody to answer that question. And so the frustration that often stems from people is they are asking for and won't just tell me, is my home going to be impacted? And unfortunately, the science is not able to give you that. What the science can give you is the probability that your house could be impacted. Now, this tends to frustrate people because people don't want probabilities. They want a straight up yes or no. But what I'm telling you is science can't give it to you. So we have this probability of surge occurring. So in this case, there's different products or iterations of this. We have this little example I pulled here, the probability of surge greater than 3 feet, which is up to my hip. So that's a pretty bad day. And then you see the colors here denote the different probabilities. So you can get everything from little or no probability to, you know, very high probabilities, over 70%. Those are the when they're released or made available in Eastern time. Now, we've done this for a long time, and we've heard that people didn't like probabilities and didn't want to sort through the probabilities and pick the probabilities. And so what we decided to do is we picked a probability. We picked a probability that we thought was most appropriate for a hurricane storm surge. And then we produced a map that shows the water level associated with that probability. And I don't know if anybody is familiar with the products or looked at our products this hurricane season. You saw a map that looked like this that was launched for the storms this year, which shows the depth of the water here. And so we found that this one graphic, rather than asking people to sort through probabilities, if we just pick the probability, and in this case we picked, I'll explain in a second which probability we picked, this was just a little bit more comfortable for people to work with. So where does that come from? It's using this P-surge. Remember, this is me shortening probabilistic storm surge. We picked this thing called a 10% exceedance. Now, this is a mouthful, even for statisticians, so I need to stop and explain it for a second. So the 10% exceedance is the surge for which there is only a 10% chance that the storm will surpass it. So let me say that again. So the 10% exceedance is the amount of water for which there's only a 10% chance that the actual storm will surpass that number. So it's not a worst case scenario. A worst case scenario would be a 0% exceedance, meaning there's a 0% chance that you can't call something a worst case scenario if there's a probability of it being exceeded or topped. So the 10% exceedance is not a worst case scenario, it's a reasonable upper bound. And I know what you're thinking, and I'm going to circle back and get to it. That sounds like an awful high number or an awful low number. It seems like you're crying wolf, but I'm going to come back and adjust that point. So this is a little bit, just in case there's some GIS folks on here, we wanted to put some eye candy in here for this. We run only the grids we need, then we merge it onto one big grid, and then we subtract this underlying high resolution topography information. So this is what's called a DEM in GIS land. So we do this. So the number one question I get from people emailing or calling is you know, how do you know how high my house is? Well, in the U.S. we have very, very, very good information regarding how high the land is. And so we're not spying on you. We can't see in your house, but we can see the elevation of the land in your community and use that to give an accurate depiction of the risk. Then the end map looks a little something like this. This is New York City area, and you get something like this where a higher color is equal deeper water. The greater, the warmer the color here, the deeper the water here. So it goes from blue is some flooding to red is over your head, and you know this is bad. Red is you know, not to put too fine of a point on it, but red's bad. And so you can see the variations here. Look at the variations here. These variations are arising due to variations in elevation. You know, the elevation is slopes and changes within this area. Here's a Texas example. So this is Houston, Galveston area. If give a little people, spread the geography out here a little bit. Now, what you notice here in this case is look how far inland the water goes. I mean, this is just a make-believe storm we use for testing. But you look how far inland the water goes in these areas, and you saw some of that bear out in Harvey with some of the experiences in Texas there. And so that's how it works. And so because it's a 10%, it's a potential. It's not what will happen. It's what could happen. Now, people are going to say, well, why don't you just tell me what will happen? And we sort of already talked about that before. Nobody on the face of this earth can tell you what will happen. They might try, but they can't do it. The limits of hurricane predictability do not allow us to say it's going to be exactly 2.4 feet of water, you know, right there. We just can't do it yet. And so what we have to do is look at all the different scenarios which could play out and give you potential. Now, I told you I was going to circle back to this question about, well, you're crying wolf here. Well, imagine in this country, do we have any tolerance whatsoever for people being rescued from critical care in a hospital, or vulnerable populations being rescued from, let's say, an elderly care facility? Do we have any tolerance in this country for people being pulled off rooftops with helicopters? And my answer to that is no, we don't. That our goal in the U.S. is to prevent all loss of life to the extent that we can from hurricanes. And we cannot let a hurricane wobble and a miscalculation result in people having to be rescued. And that's why we use this 10% exceedance. That's why we use this potential versus what will happen. Now, the downside of that is often there are places that show up in this map that don't flood because it's potential. It's not what will flood, it's what could flood given the uncertainty of the situation. So the downside of this approach is that you get places that show up in this map that don't end up flooding because the storm moves or weakens or what have you. The upside of this approach is 4 U.S. landfalling hurricanes this hurricane season, and thus far we do not have a single loss of life from storm surge. To put that in perspective, Hurricane Sandy took 41 people due to storm surge. So one hurricane before this approach took 41. 4 landfalls since this approach took none. So that's the upside. There's clearly a cost to doing it this way, but the alternative is not a scenario I'm willing to stomach. There's one more product that we've launched, the Storm Surge Watch Warning. I can explain this quickly. Here's our formal definitions for people who like definitions. I'm not one for that. I'm just going to explain it to you with plain language. If you were standing in the road and I walked up to you and handed you a map, that allowed you to deduce that you were standing in the road. That's the graphic we just talked about for the last 20 minutes. If I walked up to you and yelled at you and told you to get out of the road, you're going to get run over. Well, that's a warning. That's this product. So basically what this product does is, in situations where we feel that life-threatening conditions are possible, we go ahead and highlight it in this bright pink thing and send an alert to local officials, TV media, you via your cell phone, what have you. And in this case, we're basically saying, well, we feel so uncomfortable with the threat that we're just going to explicitly say there's life-threatening conditions possible. That's a warning. That's what the Weather Service calls a warning. And to contrast them, remember, this one is the map that allows you to deduce that you're standing in the road. This one is us walking up to you and yelling at you. So if you're ever in a situation where you see this map and you see yourself under a warning, a watch is sort of a heads up. Hey, heads up, things are not looking good. You might want to pay attention. The warning is more like, no, things are already bad. You need to do something. If you ever find yourself in one of these areas, it's time to take action. It's no longer time to search the internet for models or second guess the forecast. We take it very seriously when we paint this area pink, and it means we think there's a bad chance, there's a chance of some bad conditions happening. So if you find yourself in this warning, it's time to do something. It's time to move. So with that, I sort of given you a lot. I raced through those slides pretty quickly, give you a chance to breathe and to ask any questions that you have.
Jamie, thank you very much. Very interesting stuff. I'm sure a lot of us did not know how you do this and what these things mean, but gives us a lot to think about with the upcoming season. If you have a question for Jamie, we'll ask you to go ahead and type it in. Again, add your name and your state that you're coming from, and we'll take those questions right now. So I've got one that's come in already, and this one here would like to know, Susan writes, and she says, when is the probability flood map used? Is it used in conjunction with the SLOSH forecast or just used as a reference?
So the probability flood map is basically a derivative, or it's SLOSH is creating it. So you're running SLOSH a bunch of times, you create it. You start using that about 2 days before landfall. So about 2 days before landfall is when we would turn that process on. Now the first question that pops into mind is, why not 3 days, or why not 4 days, or why not 5 days before landfall? Because the limits of predictability of storm surge don't allow us to predict very accurately beyond about 2 days. It turns out that the noise and randomness will dominate thereafter, and you really don't get a very strong signal. So we start that about 2 days before landfall.
Okay, we're still waiting for other questions. Here we go. They're starting to come in now. North Carolina, showing the map of southeast North Carolina, the huge height seems to be, let me see, the huge height seems to be higher up the Lockwood Folly River. And you may know where that is. Can you explain that?
Yeah, so it's actually a good question. And this is one of those things that really catch people off guard is most people think, if I have to get in my car and drive to the beach, I'm less vulnerable than the person living on the beach. And that's sometimes the case, but a lot of times it isn't the case. So when you take a big volume of water, like in the ocean, and you shove it up a river, you're basically creating a funnel. So think about this. You're taking the ocean and you're pushing it up a river where the banks are constraining it more and more and more and more. And so that's sort of like a catcher's mitt or a funnel. You're making it worse. And so often surge in rivers and inland and estuaries, sometimes it's worse than the surge at the coastline. And this is a huge outreach challenge for us because, again, most people think, I have no problem. If I talk to a resident who can look out their window and see the ocean, I have no problem convincing them that the ocean could invade their house. if I talk to somebody 10 miles inland up a river, it is a tough sell to convince that person that seawater could invade their home. So that's an excellent question, and thank you for asking it.
You know, one question that comes up too, just thinking about with tsunamis, is this a similar, are there similar maps and stuff in place with the tsunami warning stuff that as these walls of water move inland?
So that, tsunami can strike within minutes or seconds, minutes or hours. Tsunami is caused by earthquake. If the earthquake is just offshore, the tsunami can result in seconds to minutes after that. And so, whereas hurricanes, generally speaking, you can see them coming for days in advance. So, owing to the different time scales, the way NOAA handles tsunamis is a little bit different than they handle hurricanes. Are there vulnerability maps out there that show what areas could be impacted by tsunamis? Absolutely. And in some cases, they have tsunami evacuation zones, just like we have hurricane storm surge evacuation zones. But the scale is, or the time scale is different, such that the products themselves are not identical.
And if you are interested in tsunamis, we have a Weather Talk webinar back in during the end of 2014. That's on our list. You can go back and listen to that. That gives you more information on those. Okay, here's some more questions. We've got many coming in now. And again, thank you, Lloyd, for that question there in North Carolina. Do you produce any flood maps for areas in the Midwest that may flood from normal causes? So I know it's different with the hurricane stuff, but are there maps out there that are produced for, I would say, probably Mississippi River, or you may even have a strong storm on the Great Lakes where some flooding could occur?
So this is an excellent question, and my response is going to benefit all listeners. NOAA does not do so let's back up for a second. So you've heard of flood insurance. All right, if you haven't heard of flood insurance, let's start there. So most homeowners insurance does not cover flood. Like if the river comes out of its banks and floods your home, your homeowner's insurance does not cover that. A lot of people don't know that, and they really get hit hard when their home floods and they don't have insurance. So to get flood insurance, you have to take a step over and above buying just regular insurance. You have to buy what's called flood insurance. Now, flood insurance is based off risk derived by FEMA. So FEMA is responsible for doing the modeling and science responsible for setting flood zones, and you've probably heard of this as the 100-year flood zone or the 100-year floodplain or just the floodplain. So you've heard people say, I'm inside the floodplain, I'm outside the floodplain, or FEMA changed the floodplain, took me out, FEMA changed the floodplain, put me in. FEMA is responsible for that, not NOAA. So NOAA is a non-regulatory agency. We don't do any of that. So the way to assess your flood vulnerability is to determine whether or not you're in a flood zone. And if you're in a flood zone, you're generally obligated with a mortgage to buy flood insurance. Now, if you buy your house outright, different story. But if you take a mortgage and you're in a flood zone, you have to buy flood insurance. So hopefully this is starting to make sense, the things you've been told over the years by your realtor or whatever. So if you're in a flood zone and you have to buy flood insurance, most people are forced to do it and they comply. If you're not in a flood zone, generally speaking, people don't buy flood insurance because they're not forced to, and they therefore deduce that they are not vulnerable to flooding. They don't buy flood insurance. Storm comes, floods them, and they're financially hardship. So my pitch to you is that everyone should be buying flood insurance. I just purchased a house a few weeks ago. Realtor happily told me I was not in a flood zone, and I promptly said, I wish flood insurance, please. And you know, you don't have to be near a river for this to happen. So look at your roads. You know, your roads have got these storm drains in them. Those storm drains can keep clogged with debris or muck during a storm. Once those storm drains flood, the road itself starts to flood, comes up your driveway, puts a couple inches of water in your house, and suddenly you got a problem. So I'm not in a flood zone, and I have flood insurance. It was surprisingly inexpensive. So there's that part of it. FEMA does that part of it, not NOAA. Now, in an actual storm, when an actual event happens, NOAA does produce flood forecasts. They don't come from the National Hurricane Center. They come from another branch of NOAA. But yes, NOAA does produce flood forecasts and flood forecast information regarding, how high a river is going to rise. Will it come out of its banks, and will it flood surrounding areas? Yes, NOAA does produce that, but I think it's important to back up first and explain the flood zones, because most people's experience with inland flooding is via those flood zones, and whether or not they do or don't have to buy insurance. So that was a long-winded explanation, but I think most people probably didn't know that, I'm going to guess.
Jamie, quick follow-up to that one there. So Northeast, think of New England, think of New York and so forth. Wintertime, nor'easters coming up. Has the Weather Service used any of your models to, I know it's a quick turnaround when these nor'easters come flying up the coast, but have they used anything there to predict where, with these astronomical tides, flooding may occur? I'm sure it's not as, again, I don't know, the flooding may not be as predominant as with a hurricane, but is there anything going on with that, or is there anything being developed to use what you guys are doing here?
Yeah, so it's a good question. Actually, a question that's come up a lot lately. So everything that I've showed you thus far today, everything that we've talked about outside of FEMA's flood zones is innovation and work that has come out of the hurricane program. So we break up NOAA into different little sections, and there's a hurricane section. So all of this has come from the hurricane program. These are all products and services developed for hurricanes. And so now the question has, now our customers and partners have said, well, that's great, but we also need it for winter storms. We need services like this for winter events. And so now there's a huge discussion within NOAA on how to take this innovation that has been developed for hurricanes and apply it to winter storms without having the taxpayer pay for all that research and development all over again. So that's what we're trying to do, is to bring that technology to winter storms, but to do it in a cost-efficient way so that the taxpayer doesn't have to pay for it twice. As of right now, it has not been done. It's future work. So while the capability is not there now, it's probably something that's going to happen over the next several years.
Great, thank you. Here's a gentleman, or Charles here, calling from Gage, Texas, wants to know, do you use rainfall estimates and hydromet levels to account for flooding from the inland sources?
Yeah, so this is actually, you guys are really savvy here. So you don't need me to know it rains a lot in a hurricane, and that water flows into the river owing to gravity, and then the river tries to flow into the ocean. So where storm surge meets the river, and the river is trying to flow into the ocean at a rate stronger than usual because it's raining, those two forces collide, and you get an especially, dangerous situation. So you've got basically the water flowing inland, freshwater flood water from the river trying to make it to the ocean, and then the ocean trying to go up the river, and those two collide. So what you have to do is you have to look at the rainfall rates and the rainfall estimates to model the flow of the water into the river and then ultimately the river into the ocean. So yes, any sort of observations on rainfall rates or rainfall amounts are incredibly critical because radar, the radar gives you a great overview, but radar estimations don't always provide, especially in tropical, don't always provide accurate depictions of rainfall. So those inland observations are really, really crucial, because that water is going to try to make it to the ocean eventually.
Great. Here's one from Boone, North Carolina, and Paul writes in, does your office produce mudslide maps for or their potential? He lives near Boone. There are mountains there. I know you get hurricanes coming up the East Coast, and there's always that potential in burn scars and so forth. Who does that, or is that being done at all?
So the National Weather Service, which is a component of NOAA, has offices, let's just call them, for the sake of simplicity, satellite offices. So little offices all across the country. And so for Boone, I'm thinking your office is probably Greenville, Spartanburg, or Blacksburg, Virginia. One of those two offices, or maybe even I think there's one in Morristown, Tennessee. So one of those offices probably handles your area. And that type of information would come out of a local, those little local offices. So the way it works, if you're curious, so we're a big office, if you will. And so we provide big picture stuff, or big picture information, which then flows down and into these local offices, or these satellite offices, who then turn it into specialized information to that region. You know, I might know a lot about the geography of North Carolina, but I don't know much about the geography of Texas. And so, you know, I'll make a 10,000-foot level forecast here at the Hurricane Center. That information flows down into the local offices, who then turn that into a specialized forecast for your area.
Okay, thanks. Here's Francis wants to know, does your model take into account antecedent rainfall?
So yeah, so yes and no. It turns out that what we just talked about, the inland rain running into the river, and then the river running into the ocean and combining with surge, is a pretty tricky event to predict. And so there's a lot of work in the research community going on right now to try to figure out how to make that connection happen, meaning the river connecting with the ocean, because the physics and the models are different. So yes, in a sense that our inland river models do. And so we have river models. They're not run here. They're run in other offices. That information does, and takes it down. And so what they do is they hand that information to us in an attempt to combine it with our forecast, or we hand our information to them in an attempt to combine it with their forecast. So our models here don't technically do it, but the forecast you get, which might not come from the Hurricane Center, the forecast you get does. So that's why it's a yes and it's a no. Strictly speaking, the model does not, but the forecast, which is more important, does.
Okay, Cindy writes, and she's got two questions. Cindy in New York. In the meows and the moms, do you use land falling paths, or can there be storm surge danger from hurricanes moving close to the coast but not coming on land? And she had a second question, and she wanted to know how many people are employed by NOAA to produce these incredibly complicated maps and forecasts. So two different questions from Cindy in New York.
Yeah, so Cindy's after my job here. So she astutely picked out that the moms and meows only include direct hits. They don't include bypassing storms or near misses, at least when you composite all the storms together. But our real-time P-surge, or our real-time, remember we talked about the real-time model does. So if the storm is moving out to sea or just barely misses you, our real-time models and forecasts predict that and show that. In terms of the second question, how many people are employed? Shockingly, very little. The National Hurricane Center itself employs probably about 60 people. The Storm Surge Unit of the National Hurricane Center, which is responsible for doing all of that modeling, all of that science, all of that technology for all of the U.S., currently employs less than 10 people. Obviously, I wish that number were different, but those are that's you have to work with the hand you're dealt, and that's what we have to work with right now.
Okay, do you have time for a couple more? We've got a few more questions.
Sure.
Okay, we're going to try to get through these here in the next 10 minutes. Brian G writes that as far as Florida hurricanes go, he talks about people, how difficult is accurately forecast storm surge on the west coast of Florida more than on the east coast. And is that because of the slope of the Gulf of Mexico? He was curious about that.
So it is. It is true that the continental shelf on the west coast of Florida, east coast of Florida are very, very different, and it totally changes the storm surge vulnerability. The west coast of Florida is probably some of the most vulnerable territory in the U.S. It's some of the most vulnerable spots, especially the areas around bays like Tampa Bay are incredibly vulnerable because the continental shelf goes forever, meaning if you drive your boat for an hour, you know, the water's still very, very shallow. Whereas on the east coast of Florida, if you drive your boat offshore, the water gets deep very, very fast. Or stated another way, the Gulf Stream comes really, really close to the east coast of Florida. So what this does is it lowers the storm surge vulnerability on the east coast and increases the storm surge vulnerability on the west coast. Now, if you're on the east coast, you're celebrating and saying, "Ooh, I'm out of the woods here," but that's not the whole story. Even though it lowers the storm surge on the east coast, it makes it more violent. So imagine it's not as deep, but it has more force and more destructive capability, even though it's not as deep and doesn't go as far inland. Conversely, on the west coast of Florida, it's more gentle, if you will, but it goes further inland and it's deeper. It's probably more nuanced than you were hoping to hear, but that's the differences between the west coast and the east coast. It turns out that makes it a huge messaging. And if you look at Irma, which basically came from the south and, you know, right up the spine of Florida, you're simultaneously trying to explain this to both coasts. So you're trying to brief people on the west coast, all that we just talked about, while you're briefing people on the east coast, sort of a totally different mental image. Turned out to be a huge communication challenge to do both coasts at the same time.
Okay, a couple more here. Tommy from Augusta County, Virginia, has two questions for you. The first is, will you have to adapt the storm surge models as climate change causes sea level rise in the future? And secondly, he's curious if storm surge can happen on the Great Lakes in a windy storm.
Oh, two very good questions. So let's deal with the controversial one first. So regardless of where you stand on this debate on climate change, and most of the debate is not on whether it's happening, but what's causing it. So I'm not going to talk about what's causing it because I think it's fair to let people look at the data and form their own opinion. But what I will say is sea level is absolutely rising. It's an undeniable, undisputable fact that sea level is absolutely rising and will continue to rise over our lifetime. We can't deny that. We can argue about what's causing it. That's a fair argument, but we can't deny that sea level is rising, which means that future hurricanes, because the storm surge is going to ride on top of that sea level rise, future hurricanes are going to be worse than they are now. Not necessarily windier, but worse from a storm surge perspective, because if you elevate the ocean a foot, that's another foot to the storm surge. Now, our modeling, to your actual question of do we account for that? Yes. Before we run our real-time model for any hurricane, we look at all the observations and we set the model with a non-zero initial condition. Usually it's a pretty small number because sea level rise is not, you know, huge over a small amount of time. So yes, we look at the observations and we set the model with a non-zero initial condition before we let it start predicting storm surge. Now, remind me of the second question.
It was about the Great Lakes. Yeah, windy storms on the Great Lakes.
So yeah, so this kind of came up in Sandy. I don't know if you remember, you know, Sandy turned into this great, big, humongous, almost wintertime event, and the Great Lakes actually had some storm surge from this northerly winds on the backside, basically pushed the water down the lakes and out of the banks. We do not do the Great Lakes. That's not within our mission assignment, even if it arises from a hurricane. That would be handled by one of those local offices that we talked about earlier, one of these satellite offices. You know, a lot of reasons why we don't do that, but I think it's better just to say that we wouldn't cover the Great Lakes, but storm surge can and does occur on inland lakes. Lake Pontchartrain is another one, Lake Okeechobee is another one, because water is water is water. If you put a force across it, it's going to respond to the force. It doesn't care whether it's seawater or fresh water. It responds to the force. So yes, storm surge does occur in inland lakes, especially the Great Lakes, which are big, and you would get that information from your local weather service office.
Okay, 3 more questions and we'll be done here. Gail from Arizona wants to know, her comment is, do you not use the term advisory for storm surge? And she says, if not, good. So.
Yeah, so it turns out that when you do social science, and that's a part of this discussion we didn't get to talk about today, is we've done, for the last 10 years, we've done a lot of social science. So social science is the looking at how people respond to and interpret information. So all of the social science that I've seen suggests that advisory is kind of comes across as sort of a weak term. It doesn't resonate with people. It's sort of like, I'm advising you, whereas watch and warning tend to have a little bit more of a stronger interpretation. So if I say I'm advising you versus I say I'm warning you, generally speaking, most people respond better to the phrase warning. So no, we don't use advisory for any of our storm surge alerts.
I like that get out of the middle of the road approach. So maybe a shout like that could, anyway, something to think about. Okay, 2 more here. Susan writes, I know the SLOSH basins are specifically designed for places, but in cases where it is not available, what methods of storm surge forecasting is used? I'm not sure.
In places where, in places where SLOSH doesn't exist, often there's little or no information available, or the information is very technical and very hard to obtain and requires a lot of expertise to stitch it together. This is why you heard the earlier conversation about, are we doing any work in the Pacific and the West Coast? There's so much demand for us to do that work because the SLOSH models up into prior to our going out there and doing work didn't exist, which meant there was little or no information about storm surge vulnerability in those areas. So we tend to be a popular group in the sense that in areas that don't have this information, people want it really, really badly, including the international discussion that we had earlier. Outside of the U.S., there in a lot of places, this information does not exist or does not exist to the citizens, meaning it's hidden or kept from them. In the U.S., I'm very proud to say that we make this information not only available, we make it easy to obtain and transparent, aka you're talking to me on this webinar. You know, you're here I am, a government official, and you're talking to me about it. So that's why it's so popular, and that's why there's so much demand for us to do these projects, is because where it doesn't exist, often there's little or no information.
Okay, 2 questions left here, and here we go. So Ralph writes in, he says, sadly, that the 2-day window does not really allow for large city centers to evacuate before so many get stuck on evacuation routes. He says, next time, if the area was not impacted, they're going to shelter in place. And I know that boy, that's a tricky one sometimes, trying to evacuate large city centers and then the hurricane veers off. So that's a comment he made on there.
Yeah, it's actually a true statement. So what happens is in places that have very dense populations, the clearance time, or the amount of time it takes to get people out, often exceeds, sometimes by a couple of days, this 48-hour window that we turn on this product. The worst clearance time that I'm aware of in the U.S., I think, is 93 hours, meaning if they started it, it takes 93 hours to get people out. and I won't say where because I don't want to pick on anybody. So imagine you're 3-4 days. Once you make the decision to get everybody out of the community, and that's because there's too many people hit the roads and clog the roads up. So one of the things that Congress is asking us to do, and we owe them a report soon on how we're going to try to do this, is they're asking us to extend that 48, extend that lead time, extend that guidance time out in time to give more notice, longer lead times to help these cities with the large clearance time. So Ralph is right. It's an area that we know we need to improve. It's an area that Congress is well aware of, and we're having that conversation now about how and whether to do it.
Okay, our final comment is from our old friend and your friend, David Glenn in North Carolina. And David, David's a Tar Heel fan, so we got to give him a little grace here on some of these things. But he wants to know if you would be interested in being a CoCoRaHS member. And if not, now's a good time to join us, his comment that he writes on that. So
is that because I just got a new house? I'm guessing that's why he's asking. So absolutely. So send it to me, and we'll find a. I'm not. He sure says yes.
He says that's the reason. He said that's it, and he wants to encourage you. So, hey,
yeah,
Jamie, go ahead.
Yeah.
Jamie, thank you again. This is very important stuff for our communities to know about. Very interesting. We'll make this again available to future folks to look at and go back online. I thank you so much for taking your time today to go through this good stuff, and hopefully we'll keep up a good record of saving lives with these watches and warnings for storm surge.
Well, thank you so much for having us, and for your listeners taking what is 90 minutes of your life to hear our spiel.
Well worth the time. I'm going to sign off for now, and for the folks out there that have been following the CoCoRaHS Weather Talk webinars, it's time for CoCoRaHS Weather Talk to go on vacation again. We've done this. This will be our second time now. We've done 21 consecutive episodes since our last break. So starting in March, we'll be taking a vacation. We'll be back later on this summer with a lineup of exciting webinars. So check back, I would say around August, to see what we have in store for the rest of 2018. And if you have an idea of one, send us an email. Let us know what you might be interested in hearing about. Finally, when you sign off today, please take the survey that's going to pop up on your screen. So until later on this summer, when we talk again, this is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now and have a great afternoon. Thank you very much. Bye-bye.